Hello everyone, let's look at this function here. We want to sketch the graph of this function. And for this curve, we are going to follow the guidelines of many of the calculus textbooks. We are going to find the domain, the first, second derivatives, critical numbers, intervals of increase and decrease on concavity, inflection points, and all that. So let's get started. Okay, so first thing that we want to do is to find the domain for this function. But before we actually do that, I really just want to rewrite this function so that it looks different. One way that I can rewrite the function is that I can remove that negative exponent by bringing e to the bottom. So what that means is we can rewrite this as a fraction, because that negative exponent really just tells us that we can rewrite this as the x is in the numerator and then the e to the 2x, right? With the negative sign, it now goes to the bottom. But when it got moved to the bottom, it does not have that negative in front of the 2x anymore. Okay, so now the function looks like that. Okay, so now we find a domain. That's our first step. So regarding the domain, let's see what's going on with the domain. So let's think about this. We have no restriction on the x for the numerator, and then we also have no restriction for the x for the exponential function here. That's e to the 2x, right? It's the domain for e to the 2x is all real numbers. Now, we have a fraction, so we also need to make sure that the denominator is non-zero, but we know that e to the 2x is never equal to 0. So that really just means that, okay, so our domain is all real numbers, right? So it's going from negative infinity to infinity. And so that part's good. Next step, we are going to do, what do we do? We are going to find the first and the second derivatives. So let's do that. So we want to find the first and second derivatives. And then we may also need to do a little bit of the simplifying, right, in general. Okay, so what are we doing? We are going to find f prime. So let's try to find f prime here. And then you may say, which one should I use? I prefer using this one because all I need to do is to use the product rule and the chain rule instead of using the quotient rule. So I'm going to use the original form with the negative exponent. So when we take the derivative of the function, the first factor will be differentiated, and then the second factor will be untouched, and we'll just copy it. So the x becomes a 1, right? So when we take the derivative, that becomes a 1. And then we are just going to copy the second factor. So we are writing as 1 times e to the negative 2x. And then now plus. And then we are going to copy down just the x. And then we need to differentiate e to the negative 2x, which will give us negative 2 e to the negative 2x. And then, of course, we got to simplify that. To simplify that, we see that there is a e to the negative 2x that's present in both terms, right? So we can actually factor out e to the negative 2x, and then we'll see what we get. So if we factor out e to the negative 2x, then it becomes e to the negative 2x here, and then you have some stuff inside the parentheses. And if we factor out e to the negative 2x, we are left with just the 1 here. So it would just be 1. And then that e to the negative 2x is factored out. We are left with just negative 2 times the x, which is negative 2x. And so that's our first derivative. Okay, so now the second derivative. The second derivative is just differentiating the first derivative. So now this time we got to use product rule one more time on this expression right here. So we have e to the, we got to differentiate this, which will give us negative 2 e to the negative 2x. And then we do not touch the second factor. So we are going to copy the 1 minus 2x. Don't forget the parentheses. Okay, that's good so far. And then we are going to just copy e to the negative 2x here. And then now the second factor. we differentiate 1 minus 2x, which will just give us negative 2. So we have this negative 2 here. And then now we can simplify. And again, we can factor out e to the negative 2x from both terms right here. So should be doing that. E to the negative 2x. And then now we have the stuff inside the parentheses. Once we pull out that e to the negative 2x, we have negative 2 and then 1 minus 2x, right? We got to distribute this negative 2 to that. So we are going to get negative 2 plus 4x. And then what do we get here? We have another minus 2, right? So minus 2. And then one more step here, we have e to the negative 2x. And then we have 4x minus 4. Okay, so that's 4x minus 4. And so that means we can actually factor out the 4 from both terms. So we get 4 e to the negative 2x and then x minus 1. And so that's all that for the simplification, right? So this f double prime is fully simplified. Now, let's find the critical numbers. If we want to find the critical numbers, we would need to use this the first derivative. Okay, so let's do that. So we want to find the critical numbers. So now how do we find the critical numbers? We have the first case for the critical numbers. We are going to set f prime equal to 0 and then try to solve that equation. So it becomes what? E to the negative 2x and then times 1 minus 2x here. And then it's being set equal to 0. Actually, that's the whole equation being set equal to 0. And actually, we do have a denominator right here, even though it doesn't look like a denominator. But then you can see that that's really just what? It's really just 1 minus 2x and then all over e to the 2x equals 0. So see what's going on here? In order for a fraction to be equal to 0, the numerator must be 0 and then the denominator cannot be 0 at the same time. And in fact, the denominator cannot be 0, right? So we have only 1 minus 2x equals 0. So that means we have x equals, if you're solving that equation, you get x equals 1 over 2. So that's our critical numbers. And then, well, this just one number, right? And there is actually the second case right here that we need to worry about. But you know that because this can never be 0, e to the 2x, so we actually have no values from the second case. So no x values. Okay, so let's do the next step. We want to find the intervals of increase and decrease and also the concavity. So in this case, we are going to look at the, let me see. So we have intervals of increase and decrease and concavity. Okay. Now, how do we do that? Because there is only one critical point, so it will actually be quite easy here in this case. The increase and decrease. And we are actually doing it on f prime, right? Because we're constructing the sign analysis chart for the first derivative. So let's do that. Let me draw the lumber line right here. And then we are going to get x here. And then we only plot that just one critical number on there, right? So this critical number, let me just highlight this so that you know that, okay, so that's our only critical number. Let me just use green on this one. Okay, so that's our critical number. Okay, so now what do? We can just pick some numbers on there. We can pick, what can we pick on the right side? One half, we can pick 1, right? So we can pick 1. Well, actually, we can pick 1,000. And then on the left side, we can pick 0. Now let's see what's going on. If we pick 1,000 and plug it into the derivative, right? Make sure that you are plugging it into the f prime. If you plug that in here, e to the negative 2x is always going to be positive, right? So now if we plug in the 1,000 in here, 1 minus 2 times 1,000, that's guaranteed to be negative. So that would be obvious. And then what about plugging in the 0? When we plug in 0 into the x, 1 minus 0, we get 1. So that's positive. And so what does that mean? That means we're having that the function is increasing before 1/2 and then it's decreasing after 1/2. So basically that's good for writing down the intervals of increase and decrease. Okay, so for interval of increase, we only have one interval, which is just what? Which is just from negative infinity to 1/2. Okay, so that's easy. And then we have the interval of decrease, which is going to be on the right side of the 1/2. So 1/2 to infinity. So that's simple. Now, we need to find the intervals of concavity. How do we do that? We are going to first look at the we need to look at the what? We need to find the potential inflection points first. Okay, so how do we do that? Actually, to organize the information, I think it will be easier if we just box this portion here. And then the next step is that we are going to find potential inflection points. So, potential IP. Now, to find the potential inflection points, we need to set the second derivative equal to 0 and see what's going on, or we try to find x values that for which the second derivative is undefined. So now we have what? We are going to look at this. So first case is when f double prime is equal to 0. So now let's look at the second derivative here. So that's really just saying that we have 4e to the negative 2x times x minus 1, and that's equal to 0. And if we are writing the expression on the left-hand side without the negative exponent, we can actually get x minus 1 over, 4e to the 2x. And that's equal to 0. And so what do we get from there? We are actually going to get what? X minus 1 equal to 0, so x is equal to 1. And then what about the second case? F double prime does not exist in this case, but you know that there are no values for this one because in the denominator, this 4 times e to the 2x is never going to be 0, so we don't need to worry about that, right? So no x values for this one. Let me just highlight the potential inflection point in this case. And then we are going to now construct the sign analysis chart on the second derivative, which is for finding the intervals of concavity. Okay. Okay, now concavity. And then, yeah, so I actually should indicate that the concavity sign chart is going to be done on the second derivative, right? So on f double prime. Okay, so let's make the sign analysis chart. So we are going to get 1 on there, right? It's just the 1 because that's the only number that we have. And then you are going to get this. Now let's just pick some numbers on here. We can, on the right side of the one, we can pick, again, we can just pick 1000, right? And then on the left side of the one, we can pick 0. And then now let's see what's going on here. Just keep in mind that for the second derivative, we are never going to get a negative number for the 4e to the negative 2x. So this is always going to be positive. So all we need to check is to check the x minus 1. If you put in the 1000 in here, that's guaranteed to be positive. So easy stuff, right? So positive. What about the 0? 0 minus 1 is negative, right? So we get a negative number on there. So now we can draw our conclusion here. We have what? On the right side of the one, we have the function being concave up. And then on the left side of the one, we are having the function being concave down. So that's quite easy to get. Okay, so now we can write down the information that we need here. So for concave up, okay, concave up, what happens? We have 1 to infinity, right? 1 to infinity. And then what about concave down? Then it's going to be what? It's going to be from negative infinity to 1, as you can see from the sign analysis chart. Okay, so that's good. And then the next step, we need to find the local maximum and local minimum here. So let's do that here. This is what, I don't remember. This is part D, so we got to do part E, right? So now part E. Local, max, min, and then also the inflection point. So regarding the local max, do we have a local max right here? Let's check the sign analysis chart for the first derivative. So you can see that the function it's increasing, and then after it we go past the 1/2, then the function becomes decreasing. So now if you look at the graph, then the graph looks like this. You see what's going on here? That actually is a local maximum. So we do have a local maximum, which would be to plug in the 1/2 into the function. Okay, so local maximum. And then in this case, we got to use the original function to find the y value. So let's see. So the original function is this one, right? X over e to the 2x. So let's just do that. Okay, so going back to here, we are going to get actually, I'm just going to use the original form. So x times e to the negative 2x. Okay. Well, do we need to plug in the 1/2 in there? And then we do the calculation. And I'm not going to spend the time doing all the simplifying. So we are just going to get 1/2e. So if you want a point for this one, then actually for the point, we are going to get what? We're going to get what? What is that? The point would just be 1/2, right? 1/2. And then what is that? The y value is going to be 1/2e. So that's our local maximum. Now next, local minimum. We actually have no local minimum. So we don't have anything for local minimum. What about the inflection point? Do we have an inflection point? Let's check the sign analysis chart for the second derivative. There is a change of concavity, and then because the function is defined at 1, so that's a inflection point. So that means all we need to do is to plug the 1 in there. Then we are going to get e to the negative 2 times 1. And then we have 1 here, and then 1 here. So that's easy to calculate. If you do that calculation, you are going to get, what is that? That's e to the negative 2, right? So 1 over e squared. And if you're putting it as a point, then you are going to get, what is that? That's 1, right, as the x value. And then 1 over e squared. 1 over e squared. 1 over e squared. Yeah. Okay, so that's our inflection point. And then we also want to analyze the behaviors near the asymptotes if there are asymptotes for the function. So let's check. Let's check the asymptotes. So this is part F. We want to look at the asymptotes and behaviors of the graph near them. And we want to see what happens. And actually, because the denominator, if you go back to the original function, because the denominator is never 0, so we do not really have any vertical asymptotes. Right? We cannot have the denominator approaching 0. So that means no vertical asymptote. So that means we have VA. For VA, there is none. Right? There is no number that you let x approach to where the function is approaching infinity or negative infinity. That's what happens. Now, what about the horizontal asymptote? For horizontal asymptote, we need to check the two limits right here. So one of them is that we need to take the limit as x approaches infinity of the function. So the function, of course, is x over e to the 2x, right? So now I'm using the form without the negative exponent in front of without the negative sign in front of 2x. And so we can evaluate this one by using L'Hopital's rule. We're using L'Hopital's rule. What happens? Then we are going to get 1 over 2e to the 2x. And as x goes to infinity, then we actually will get 0. And then also I want to indicate the direction for this limit. Because 1 is positive and 2e to the 2x is never negative or 0, right? When x is approaching infinity, this is also positive. And so that means we're approaching 0. I mean, the function is approaching 0 from the right. Okay, and then I will explain why I want to indicate the direction here. So now the other direction for the limit. Negative infinity, where we have the same function here, e to the 2x. And then we can use L'Hopital's rule right here. Right? And then we are going to get what? 1 over 2e to the 2x. And now let's just think about that. If x is approaching negative infinity, this will give you what? It's going to actually give you... Oh, actually, we cannot really use L'Hopital's rule. The reason is, I was just thinking on here, so sometimes I get distracted. So always, this is actually a good lesson. So make sure that we check. If you plug in negative infinity, the numerator is going to be approaching negative infinity, but when we plug in negative infinity into this x right here, this is actually what? This is actually, you can just imagine. So let me just do some scratch work here. You don't need to write this down. So just imagine that we have 2 times negative infinity, which is just negative infinity. So that means we are getting a form of negative infinity over e to the negative infinity. And that's actually, if you just think about it, if you're taking the reciprocal of this e, then you're actually going to get e to the infinity. So see what's going on here. E to the infinity is infinity. Infinity times infinity is also infinity. And then we are going to get a minus sign in front of the infinity. So the answer for this one is negative infinity. Okay, so you really got to be careful, right? We cannot blindly apply the L'Hopital's rule. Okay, so what's going on here? If we are getting infinity or negative infinity as the answer, we do not really get a asymptote from that limit. But then now this limit actually tells us that there is a horizontal asymptote, which is y equals 0 in this case. So we do have that, right? Y equals 0. Let me just put it here. So it tells you that the horizontal asymptote is y equals 0. Okay. Now last one, this one is just basic algebra right here, but I should just still just do that just to check. We have the intercepts, right? We need to find the intercepts. And then you know how to find intercepts, right? You plug 0 into the x and you plug 0 into the y and then solve for the other variable. And eventually you are just going to get, I'm not going to spend the time showing this one, but then the intercepts, actually, there is only one intercept that's both the x and the y intercept. That's actually 0, 0. That's the origin. Okay, so now we have found all the information that we need for this. As you can see, that's a lot of work. Okay, so now we can start graphing the function. Okay, so what do you do first? We are going to plot all the points first. So all the points. 0, 0 is the easy point to plot. So let's just plot that on there. I'm going to use blue to graph. I'm going to use the blue color to graph the function. So we get the blue over there. Now, what are some other points that we have here? Some other points that we are having, it's really just the, there is a 1 over 2 and then 1 over 2e. The other one is the 1 and then 1 over e squared. Okay, now it's a lot of trouble because we may not have the value for those ones, so we need to use a calculator and then do an approximation. You can actually approximate by hand, but calculator will be easier in this case. And then also when we do our graph, we need to set up the scale correctly so that it will be easier for us to graph. Okay, so I would say that those numbers are small. Think about e being 2.7, right? So you get 2 times 2.7, that's 5 point something, and then you are going to do 1 divided by 5 point something. So you're going to get a small number right here, and then same thing here, you're squaring the 2.7. And in this case, you're going to get small numbers. So for the y values, we probably don't need that to be 1 because it's going to be small numbers. So I can actually put the 1, let's say right here, 1, 2, 3, 4, 5. So we break it into 5 of them. So I think that's 5, right? So this one is 5. So we call this 1. So we set up the scale right here. And then, so that means we have 1, 2, 3, 4, 5. So we have the negative 1 right here. So okay, now for the x, we don't need to use the same scale as the y-axis right here, depending on how you want to assume it, but we do need to make sure that we are using the same scale for the whole y-axis or the same scale for the whole x-axis, right? So let me think. So maybe we can try, there was a 1/2 for the x value, maybe 1 right here. I think that may be a good idea. So let's just try that and see what's going on. Okay, so we will just do the 1 here. This is 1. Okay, now let's plot those points. But I don't want to do a calculation first. Let's just do the calculation right here. We have 1 over 2e, right? 1 divided by 2 times the e. And then so we are going to get this number. This number is actually 0.184. Okay, so if you put that in your calculator, and then I also want to do e squared, right? So e squared, and this number is going to be 0.184 135. Okay, so now let's plot those points. 1 over 2, 1/2, which is the x value right here, and then 0.184. That's almost 0.2, right? This is 0.2 because I break the 1 into 5 boxes right here. So 0.184 is about here. So we get the point there. So that's actually our, what is that? That's our local maximum. Okay. Now, what about the purple point? The purple point is actually the inflection point. So that's 1, and it's 0.135. So we know that that's 0.2. So 0.1 is halfway, and then it's slightly greater than 0.1. So it's like here. So we get that here. Okay, so that's good. And then now asymptotes. Let's graph the asymptote. Asymptote is, there is only one asymptote, which is the horizontal asymptote, y equals 0. That's actually just the x-axis. Okay, so let's graph that. Okay. Yeah, so now that's that. And then let's see what's going on here. We know that the function, when x is approaching infinity, the function is approaching 0 from the right side. That's really just saying that your y value are all positive, right? So in this case, you know that the curve will be like just going this way and then eventually approaching the horizontal asymptote, but it's going to be above the horizontal asymptote because of this plus superscript right here. That tells you that the function, they're all positive, those values that you're getting. Okay, so now we can actually just graph here, and we should really just do a quick check on what's going on right here. For the function has been increasing before 1/2, and then it starts decreasing after 1/2. So after 1/2, it starts decreasing. Okay. So what does that mean? That means we have the function after it reaches the local maximum, and then it starts going down. But then before the 1, it's going to be concave down. So we want to make sure that it looks like it's concave down right there. So let's do that. Concave down. Okay, so that's concave down. And then also we are going to connect the points, right? So we are also getting a concave down right here. And then it feels like the graph does not get connected. So concave down. Okay, so that's good. And then now it becomes concave up after the 1. So we also want to graph it correctly. So concave up after. Okay, so that seems to be good. And then what about this side here? What about this side here? Remember the domain? It's all real numbers. So we do have stuff on the left side of the y-axis. Now, we just need to look at this here. When x is approaching negative infinity, then the function is approaching negative infinity here. So that's really just saying that, okay, so we are going to go down forever for the graph. So now just make a smooth curve right here. If you want to make it more accurate, you can probably plug in -1 into the function and then do the calculation. But our goal here is to minimize the amount of work that we need to do for plugging in values to the function to find the points, right? So right now, I'm just going to just get the general shape. It probably will not be too accurate. We're getting the actual points on there, but the shape is going to be correct. So what are we doing here? It's going to go down to infinity. And then so you know that in the denominator, the exponential function is going to increase a lot faster than the linear function, right? And so when x is approaching negative infinity, then you are going to just go down really quickly. So let's do that. Let's just make it a smooth curve, and then we'll go down like that. It's not a straight line, still a curve that's concave down, right? So that's concave down, and then there is a change of concavity. So let me just label my answers right here. There is a horizontal asymptote, y equals 0 right here. And then we have a, what is that? That's the local maximum. and then we have a inflection point, and then their coordinates are right here. Okay, so that's it for this problem. And if you like my video, please subscribe to my channel and give me some support. Thank you for watching. I will see you next time.